All right. Okay. So today we are going to move on from the pipelining that we talked about in the lecture last Wednesday. So let's do a quick recap on what is pipelining. Basically, if you look at this diagram again and again, like this is the third, the fourth lecture that you see the same diagram again, right? Whenever we talk about pipelining, it's essentially the goal, the motivation behind why do we care about pipelining is, let's say you built a CPU for a program, right? And you basically your goal is you want to utilize everything inside it as much as possible in every single cycle. So one way to do that is to actually have pipelining, right? Sorry, my cat just walked on my keyboard. Basically, you can then actually break these logically down into multiple stages of how you process an instruction. You would first fetch your code, right? And between fetch and doing something else, then you can have another instruction doing the decode, right? Another instruction doing execute, another instruction doing the memory, and another instruction that trying to commit and write the result back. And this is the key, the core behind pipelining, right? To actually apply pipelining correctly, one thing you want to do is you need to actually add a pipeline register. Right? What it is basically it store all these intermediate values because as we stress again and again and again, the only thing the programmer see is whatever finish, right? Instruction in the write back stage. Those are what the programmer see. They don't see something, anything in the middle, but somehow you are processing the future instruction, which means that you need to store these intermediate values. Think of it as a temporary variable that you store inside the program. So the pipeline register will store all these, one for fetch, one for decode, one for execute, and one for memory. And the write back stage, you actually write the actual register files, right? So these store internal data that are related to its current instruction. And as I said, they can be costly, but it is actually this whole design is cost effective enough that you would use and apply it on all processor that you see nowadays. And when you have pipeline register, I represent it as this a vertical red box here, where whenever you have wires going across each of these boxes, you are actually storing these intermediate values across different stages of the pipeline. So one of the question that I would like to stress is, let's say you look at this program, right? How many cycles does it take? We actually have the sample from the last lecture, so I'm gonna repeat the same example again. But if you look at this particular instruction, because there's no dependency, you would then I think this take 9 cycles. So if you go through the same example again, it should be around 9 cycles if I'm not wrong. And there are actually some reasons that can make your execution time longer. The earlier example, if you have a different instruction with the same type 4 instruction, you can actually end up with more than 9 cycles, right? Sometimes you have a long memory latency that you have to go access the memory. Sometimes you predict a wrong branch. We briefly talk about this toward the end of this class. And the one thing that we talk about mainly in the last lecture, including today, is data hazard. What is data?
I think you're muted.
Hello?
Can you hear me now? Okay, something is wrong with my laptop. I'm using my desktop audio. When did I get disconnected? In the beginning? Oh, is that when my cat just walked across my keyboard? Okay, 5 minutes. All right. So sorry about that. Let me move back here. Yeah, let me move back. Go back to my slides here. Is it around here? Yeah, sorry. I think my cat typed in something which I have no idea what button she press. So sorry. So okay, oh my god. So I think it's about here, right? About process design way in the beginning. Okay, so now you can't see the screen. So she disconnect everything. Share the screen. All right. Is the screen back? Is it good now? Yeah, I'm trying to share the screen. It refused to let me share for some reason. Let me disconnect and connect again. I'll be right back. Please. And then you should see my screen now. Is it back now? Okay, yeah. Sorry, my cat broke everything. Oh, it's still recording? Perfect. All right, I think she kind of disconnected the internet. That's what happened on my laptop. I'll make sure she can't walk across my keyboard again. Sorry. Uh, yeah. Okay, so basically we talk about processor design, where we have pipelining. So these are from the last lecture, where we can actually have fetch, decode, execute, memory, and write back to try to maximize utilization. But to actually implement this, you need this thing called pipeline register, where you actually, instead of letting the programmer see all the stages, so you actually let the programmer see what instruction finish. Whenever instruction finish, you see that. So the rest of the instruction inside your pipeline need to be stored in some temporary variable, something in the middle, right? Intermediate variable. So this is called pipeline register, where you store all these intermediate states, one for fetch, one for decode, one for execute, and one for memory, and each of these store the internal data that are tied to that instruction. You need to do that for your assignment too. So this can be costly because you're adding more structure, but its performance improvement way outweighs what you have to pay for the in terms of the price, right? So all your processor you buy nowadays, every single item, most of them would be pipeline. How complex? That depends on the type of processor. The desktop is way more complex than the older browser that you use for Nintendo Wii or the PlayStation 2, right? And here's the pipeline register. Every time you have this red thing go across different wires, you need to store the data that specifically for that instruction. And we talk about how many cycles does it take. This generally, I think this take 9 cycles. If I'm not wrong, I'm pretty sure it's 9 cycles. But if you go to the last lecture, we went through this in detail. And then we talk about the cost of instruction stall, which can be when you need to go to get your data from the main memory, that can take a long time. When you have branch, if else, right, or for loop, that can also take some time. We talk specifically why in the toward the end of this class. The data hazard, which is what we ended up talking about last lecture, where you have some instruction like this, right? The red things here are zero, the first line generate the result for the second line multiply. R3 then generate the result for the XOR. The XOR results in R6 would generate the result for the last add, right? The load, you load that address into R8 and add the last line again, use R8, which means that you need to finish the first instruction before the second, the second instruction before the third. If we assume each of these operations can take more than 1 cycle, what can happen is you need to stall your pipeline, right? This is called dependency, and this is how you deal with it, right? So what you do is you pause the future instruction that are waiting for the data until that data get written to the register files. These can take some time, but it's to make sure your program is correct. So the content of this class, the majority of the content we talk about this technique called data forwarding, it actually allow you not to pause. It allows the pipeline to go as fast as possible. But let's talk about what you need to do when you have to pause, right? Over here, you have instruction n plus 1, and n plus 2. Instruction n is in the execute stage, trying to generate the result for n plus 1. Let's think of it this way. Let's say instruction n is an add instruction that creates the new value for R1. N plus 1 needs R1 because what N plus 1 is doing is R1 plus R2 and then write the result to R3. Then it means that N plus 1 is waiting for the result of N. And the result of N is not available until you're here in the write back stage, right? Right here. I can't use my pen. In color, right? In the write back stage is when instruction N finish. So in the next cycle, right, and move here to the memory stage, as denoted in the yellow text here, you insert the bubble. The bubble means that you do nothing in execute. Then n plus 1 and n plus 2 stays there in the fetch and decode. And then in the next cycle, I'm going to use a better color blue here and now move to write back. you have this bubble move here, and then you insert one more bubble right here. Instruction n plus 1 stay here, n plus 2 stay here. Can I have result for n plus 1 now? While n is in write back. Or do I wait one more cycle until the register files got the data? Do I insert one more bubble or do I pause? Do I insert one more bubble or do I proceed with n plus 1? Did someone answer in the chat that I don't see? No? Oh, can I go? Can I ask the question again? Yes, sure. So over here you have n, instruction n, right, in the write back. So n is here. Bubble here in the memory, bubble here in execute, n plus 1 is here, n plus 2 is here. In the next cycle, where is n plus 1? Is it going to be in decode still, or is it going to move to execute? So actually it stay in the decode. The reason behind that is this instruction and haven't finished. It haven't finished. So it still haven't write the data back to register file. It's trying to write the data into register files. The data is not updated yet until the next cycle. So the next cycle, what happened is instruction and finish, right? And move out. Done. Okay. And then bubble right here. Bubble right here. And bubble right here. And now result is ready, right? So the next cycle, I'm going to use a different color again. Now let's use black. Now n plus 1 stay here, bubble here, and bubble here. And then n plus 2 now move here, n plus 3 can be fetched. Any questions so far on why? Why do I have to wait until n finish the write back? All right, so here is generally what you have to do. These are the condition, and this is actually important for your assignment too. Basically, you need to determine when you have to insert the bubble, right? So the stall condition is when, right? When you have the distance between decode and write back. What's the distance between decode and write back? That's 3 cycle, right? That's 3 cycle. So the instruction need to stall when the dependent instruction is still in the pipeline. Let's say this instruction 1 and 2 generate the result like this, right? So if the distance of 1 and 2 is still less than the distance between decode and write back, which is 3, you still have to stop. You still have to stop, right? Basically, in the general case, you need to stall the decode stage until data is written back to the register files. That's the kind of like the rule. Here's like the condition. This is almost like a solution, like a big part of your assignment too. This is the one where you can tell, okay, if my source need this in the register that come from the destination from each of these states, right? So the subtext here, this is the stage, right? This is the pipeline stage. Over here, dependency is destination generate the output for source. Basically, source means that I need that data, and then destination means that, hey, future instruction somehow still generating that data. So based on this, basically, if you need the source and the source is still not in write back, you wait and stall. That's it. It's as simple as that, right? And here is a table that determines for each type of instruction. This is basically a compute that use register, right? This is load instruction. This is store instruction. Load and store basically deal with the memory, branch, jump, and jump with the register. You notice that everything here is stalling in the decode stage. Right? That's when you realize I need that register. I need that register. And that's the first time you realize that, okay, I have to stall. For how long? Until the dependent instruction finish the write back. Until the dependent instruction finish the write back, right? And when is safe to assume the instruction? Can someone answer that question? Because I just said that less than 1 minute ago. When is it safe for me to resume my instruction from the decode, move them to the execute? After you complete write back, yes. Basically, when the dependent instruction finish writing back, then you can move on. Right? Sometimes it's only one cycle. So when is that only take one cycle? So this can come in three variations, right? The one that you stall for one cycle. You can stall for 2 cycles, and you can stall for 3 cycles. So when will I only have to stall for one cycle? Can someone tell me what's the condition for that? Distance is actually 3. So let's put it this way. Instruction in the write back, right? In write back is n, and then n plus 1 here, n plus 2 here. So this is memory. This is execute, right? And this is a decode, n plus 3 decode. And somehow this n generate result for the one in decode, which means that distance is 3. You wait until we finish the write back, and then decode can move on. So you insert one bubble. How about the one for 2 cycles? Which dependent instruction, for the dependent instruction, what stage will that be in if you need to stall for 2 cycles? Nope. If it's in execute, you stall for 3 cycles. What's in the middle of execute and write back? Yep, load and store. So if it's in the memory instruction, you stall for 2 cycles, move them to write back, and then move them out of the write back, right? So if you're still confused, please check out the lecture from last week because I noticed a lot of you are actually not in the class last week. I can't help any more than this. If you're not gonna go to office hour asking about the questions, if you're not gonna attend the lecture, what else I can do? I'm serious here, right? Because it's your job to attend the lecture. And in the lecture, I'm sure you repeat the question multiple times. So if you actually listen to the lecture and if you are confused, ask the question in the lecture. That that's how you learn. You can't just magically say, hey, I'm gonna watch YouTube. And then magically, when midterm comes in, one day before the midterm, you would hope that you can do the midterm. I can guarantee you my midterm would kill you. That I can guarantee. If you do that, my midterm will kill you. All right. So if you're still confused, please check the lecture video from last week and ask me during office hour, outside of office hour to email outside of office hour through Discord. Those are also okay, right? But if you have time, please come watch the lecture online. And if you have questions, ask the questions. All right, so that's it for the stalling. Like we actually can do better, as I said earlier. We can do data forwarding. So data forwarding is as the name suggests. What does forwarding mean in English? It means you moving the data, right? It's data forwarding. So you get the data, grab it, and move it forward. So the observation is, let me ask you this. When is the first time, let's say I need R1, let's say I need R1, and R1 dependent instruction is actually an add instruction. So when is the earliest time that I can see the result of R1? I'm not talking about when you write it back to the register files. I'm talking about when is the correct value of R1 becomes available inside somewhere in my logic. So there can be three choices: execute, memory, and write back. Right? And if you think about it, right after the ALU, I already have my result. So it just in the wire, physical wire, it just stayed there. The only issue we discussed so far is because we haven't commit them in the register files yet. Like we haven't write it back, but the data is there. So the data becomes available since the execute of memory. Right? What type of instruction would have the data available in the memory state? You can have compute, you can have load store, and you can have a branch. Which one is the one that you have the results in the memory stage? Why compute? So compute have the result in the execute actually. Once you go through the ALU, right, you're done. When we so I think that might this might looks confusing, but once we show the big picture, like the design, I'll tell you why. Right after the execute, we actually have the data, but for the memory stage, those are load store instruction. When we have it, you would then ask like, why do we wait until the write back? Like we have the data, and this is actually the idea behind data forwarding. When we have the data in the pipeline, forward that into the next instruction, right? Why you even have to store and insert this bubble. So for each instruction, check if the source come from the earlier instruction in the pipeline. If yes, whenever I know that the data becomes available, I forward it right away. No need to wait until the write back stage, right? These solve the raw dependency. Read after write. The benefit is way better performance. And this is the diagram, right? So whenever I have a compute instruction, I think the reason why a lot of you say so right here at this point, what data is out of that point, out of that wires? It's the result of instruction. Let's say this is instruction n, right? And this is a compute instruction. It's actually just compute. Load and store. So load instruction. When you load something, you got it from here, right? You are getting something from the main memory, so it's not available until the end of the memory. But the end of execute, these are compute instruction. And these are memory type instruction. Anything that you need from the memory, you got it during the memory stage. Otherwise, right after the execute stage, you got the data already. Right? So over here, over in, let's say I have instruction n plus 1 and n generate result for n plus 1. Do I have to stop if it's a compute instruction? Do I have to stop if it's a compute instruction? No, that answer is correct. Basically, you don't have to stop. What you have to do here is basically, I like, okay, I know that this is my data, right? And I know this is actually originally what I need, right? I want, okay, let me use a different color. Let me use blue, right? This is where you need to actually have the source of your data, but you know that it's right here. You don't have to wait for the write back. So what you do here is you actually attach the physical wires, right? Over here, your design, each line here are wires. So what you do here is you attach the wire, hook it from here, sneak it around somehow so that you can put it as an input over here. This select line is of 1 and 2, 0 and 1. Now you have the next input, right? So which one are you selecting from? 0, 1, or 2? Yes, you select from source 2. So basically this would have the value of 2, right? It means that, okay, I have additional inputs where I have it forwarded from this cheating path directly out of the ALU. And I'm going to select that because I know that's my data, right? That's my data. Any questions so far on why for data forwarding? In this case, if it's a compute instruction, you don't have to stall. You just find this alternate path, send the wire, like actually add the physical wires connecting the output to this mux right here, and then you can actually move on. So any questions about this? Because then I'm gonna show you 3 examples when distance is 1, when distance is 2, and when distance is 3. All right, seems like no one asked any questions so far, so I hope the explanation is clear now. If there's still question, feel free to let me know. All right, so when distance is 1, when distance is 1, it means that I have instruction n right here, n plus 1 right here, right? And I just show you if it's a compute, you can forward it from here to here. What if it's a load store instruction? It's, what do I do here? If distance is 1, n plus 1 need the data from n, and this is the load instruction. What do I do? You forward it from the main memory, which means, right, okay, for the compute instruction, you forward it from execute and you don't have to stall. The next cycle n move on, the next cycle n plus 1 also move on. But if it's a load and store n move here, this is a bubble. N plus 1 stay here, right? Because I have no way to forward my data. I have no way to forward my data. Everyone with me so far? Because I have no way to forward the data, my data start arriving right here, right? My data arriving right here. So over here, one thing you can do is from here, you forward it right here to here and here. We put 0, 1, 2, right, 2, and 3. Now, instead of selecting line here, instead of asserting value 2, now you put in 3 because you said 3 is that data coming in from the memory stage. All right, so is everyone clear so far on when distance is 1? If you are dealing with compute instruction, just move on and forward it from execute. If it's a memory instruction, you stall 1 cycle. Okay, so there was a question, sorry, I think from here, right? There was a question, why do we pick this second input instead of one, right? Is that a question? Sorry, I missed the question. I'm so sorry. So the reason why we put second for the select line right here is if you put one, you are going to actually get the data right here from the register file. If you say select is one, it means that you're gonna get the old value. But because we make this forward path, right? So forward path from execute stage, hack it so that it insert right into the mux here. So the select line need to select that cheating path. Basically, it's like you provide a cheat code, so you need to select the proper cheat code. So does it answer your question? So if you pick one, you're gonna get the wrong old results because you haven't write it back yet. So you need to say, hey, I use that path. I use that cheating path. Okay, so in the case that distance is 2, it means that right now, right? Oh, for jump and branch, that's a great question. For jump and branch, the way you style it is a little bit different. We're gonna discuss it toward the end of today. So please bear with me so far. For jump and branch, there is a little bit like special condition that you might have to stall for longer, or you might have to stall for less, depending on the design. Okay, so when distance is 2, this is what you do. This is what happened. This instruction n, this instruction n plus 1, n plus 2, right? And in this case, n is giving the result to n plus 2. All right. If it's a compute instruction, what do I do? If it's a compute instruction, I'm just gonna get it from here, right? There's a wires that coming from the ALU into my pipeline register, so I've used the same thing. Forward it again to here. So for the select line, let's say you have 2 and 3 used already, right? The input 2 and input 3 are used by the case where distance is 1. So over here, what would be the next number? 4. Yeah. So over here you select 4 because 4 is now corresponding to this particular input. For the case you have the memory instruction. Memory instruction is the data is arriving right here, right? You can do data forwarding again. Put it here. And let's say you put input 5 as over here. Now select line would pick 5, right? Depending on the type of instruction, you know that it's from the different source. The hardware, as I said in the first lecture, hardware is dumb. It's super dumb. Every time you have new wires coming in, you need to select that new wires. So over here, it will select 5, right? Because that's additional wires coming in. Say, hey, I now forward it from the memory stage. My next question is earlier on when I said input 3 is actually forward from the memory, input 5 also forward the memory that are from the memory stage. So can I share the two inputs? Yes, you are correct. Basically, the answer is yes. You actually don't need to put in additional wires. You already have that wires. So this become what? 3. Yes. This is still the same input 3. Because your design is not dependent on the instruction, it dependent on the actual hardware. You already have these wires connecting between the output of memory to the input of my decoder. So I would then use and piggyback the same input. There's no need to add one more wires that do the same thing, right? So you select 3. All right, for the distances tree, same steps here. So hopefully you got the idea. Now, if it's a compute instruction, you forward it from here down to here. Now that you use 1, 2, 3, or 1, 2, 3, and 4 already, so what input is this? We can say this is 5, right? You select 5. And if you are forwarding it from the memory stage, which is right here, it's a different wires now. So this go to 6, right? So you have 5 and 6. Any questions so far? Any questions so far? So my question is, why do we need new wires there again? Because this is now forwarded from the write back, not the memory. It's a 2 different instruction. If you forward it from the main memory, it's a different instruction. It's a future instruction already, right? So my question is, am I missing anything that is labeled red here? This register, and I need it. And Champ actually already asked about it. It's branch and jump, right? Branch and jump. What does that involve? It doesn't involve the typical thing in the register file. Branch and jump is whatever value you want to put in the PC, right? Whatever value you want to put in the PC, which means that you are somehow going to then forward, right? Forward these things down to the PC, right? So we're going to talk about this in a bit. My next question is, what type of instruction besides branch and jump? Okay, yes. So that's a great question. So there was a question about like, does this mean we can have virtually infinite amount of select line? Yes. You are the hardware designer. Put whatever you want. Be mindful, right? Be mindful that every time you add something in, you need to actually dedicate some cost to that. So ideally, you want to minimize the use of these additional wires. But if the question is like, can I keep adding more things? Yes, you can keep adding more things if that justify the performance over cost. So hopefully that addressed the question. Sorry, there was 2 chat windows and somehow my laptop chat is ahead of my desktop chat. And this happened occasionally with WebEx. So if I miss your question, it's not like I intentionally don't see the question. I actually need to look at two screen. So hopefully that answer your question about having multiple select lines. You can have as many as you want. All right. So another version that you can forward things in is what we've been doing is we forward it from here to here, right? A different way you can forward is you can actually forward it directly from this pipeline register, right? From the pipeline register, which is right here, down to the earlier stage. From the simulation point of view, which is your assignment, it doesn't look that much different. From the actual logic point of view, these can look different because you have different stores. These will located at different place on your CPU. So you are actually drawing the wires from different locations here. And because wires cannot cross each other, because you short the circuit, right? So you can have a short circuit. So somehow you need to kind of like sneak around the wires going around things. So having multiple versions to do data forwarding helps here. All right. So in terms of data forwarding, what is the main cases that you have to solve? instruction using the same register, that's still you might not have to stall. But if the dependent instruction is generated in the memory state and the distance is 1, then you have to stall, which is what this table says, right? If you have compute instruction produce the result right in the execute stage, so you can forward to the earlier instruction always, except for jump here. This means you have to stall 1 cycle. Whenever you have to use and produce that are not on the same line, it means you stall 1 cycle. This means you have to stall 1 cycle. This means no stall needed, right? So if the next instruction is a jump to certain register, and that register is produced in the execute stage, or like something like this, it means you stall 1 cycle. If that register is produced in the memory stage, used for jump, that's 2 cycles stall, because you need to wait until you know the value of your register. If you produce the result from the memory and use it for a normal adder instruction, then you wait 1 cycle, right? And from here, right, as I said, the one case when the pipeline stall is when you produce an instruction in the pipe, like basically over here. When you need to forward here, here, and here, and then one more case right here. So all the red lines, if you have back-to-back loads, for example, you have to stall. Any questions here so far? All right, so if there's no question here so far, the next thing I want to tell you is about the trade-off of data forwarding, right? So the benefits is way fewer stall cycle. This is going to give you a lot of performance. This is actually one of the key things back in the like 80s to 90s. This is one of the key techniques that people use to make processors faster. The downside is this can be complex. You need to add a lot more wires. You consume more power and it costs more die area. Your CPU actually get bigger. And if you think about nowadays, you are looking at the CPU with 30, 40 different stages, right? So when you have that many stages, data forwarding can get crazily complex. Right? Crazily complex. A lot of times you actually requires a program to draw the diagram for you. It's that complex, right? It's actually one of the research area, actually, how to generate the correct way to lay out all the circuits. Uh, and as Champ suggests, right? So what about branches? Branch is another piece of big beast that we need to beat to get performance, right? So we will talk about the majority of branches on the lecture on Wednesday, but I'm gonna quickly introduce the concept of branch prediction. Branch is actually one of the problems that you can have instruction stall, right? Here's a sample code, right? Let's say you have if a 0, do something, else you do something else. These are branches. Any questions about why are these branches? This should be pretty self-explanatory. But any questions? So the way you handle branch, as I said earlier, if you have dependency, you can start the pipeline. But one of the quick thing you can think about is you need the branch when you fetch, right? You need to know where are you fetching. Are you fetching here in the do something one, right? Are you fetch here? Are you fetching this code? Are you fetching this code, right? Which direction you're fetching from? That is called uh, basically that's the value of the PC that you want to take next, right? So my question is, are there better options? Can we do better than just always, whenever we have branch, we are going to start a pipeline? Predict. Yes. Yes, you can predict. So we today we're going to talk about some basic way on how this can be handled, right? The simplest way, as is it, we can start the pipeline. The next method is we can blindly guess. You can use educated guess, and then you can do more things that we're going to talk about on Wednesday. Right? These I'm not going to talk about these at the moment. I'm just going to talk about the first three things, the simple ones. The first solution is stalling the pipeline. So over here, you have instruction n right here, right? N minus 1, n minus 2, and n minus 3. And somehow, when n is in the decode, and say, hey, I'm a branch instruction, you have n plus 1 over here. If I have to stall, what do I do? If I have to stall, what do I do? So what you do is move n on, right? Because there's nothing wrong with n. So n plus 3 is done. N plus 2 is here. N minus 2, my bad. N minus 2 is here. N minus 1 is here. N is here. And you insert the bubble right here. You stall, right? And then n plus 1 stay here. Are you all with me so far? Basically, you now put in one bubble to stall. Okay. So let's say that it branch this instruction branch if R1 is less than R2. So you're gonna get the result right here. Right? You're gonna get the result from right here. So at this point, you know, basically now you know that okay, which part do I branch to? So in the next cycle, you know what exactly you have to do. N plus 2 move out, n plus 1 is here, n minus 1 is here, n move here, bubble move here. If you are actually going toward n minus 1, you keep n minus 1 right here. You keep n minus 1 right here. Otherwise, you change to, so pick some value. Can someone pick some value that you are branching to like some address? Give me some address. Can be any address. All right, again, 0. Okay, it's either this one or this one. Basically, it's either n plus 1 or 0, right? And let's assume that you're picking 0. So you're going to switch to the value 0. The IR is now 0, right? In the next instruction, oh, actually, then in the next instruction, you move, right? You move n plus 1 out. Oops, wrong color. We use orange. So move this out and move here. Bubble here, right? Bubble right here. And now instruction 0 move here. Instruction 0 move here. And then instruction 4 now move here because it's easier plus 4. So basically you insert the bubble until you know exactly where you're branching to. Once you know that, you forward the data, put in the correct PC value in the next cycle, then you can move on. So that's the naive solution. So how many cycles does it take to run this code where you have the branch right here? You branch if R0 and R1 is not equal. So let's do this line by line. For instruction 1, when will I finish instruction 1? Fetch, decode, execute, memory, and write back, right? And this is when R0 is generated. So you know R0 and execute. You fetch over here. You decode, right? Instruction to fetch and decode. By the time decode comes in, decoder, oh crap, this is a branch instruction. Right? This is a branch instruction. What do I do? Well, I'm gonna execute, right? So that I know the result of my branch. Memory and write back. So instruction to proceed normally because we do data forwarding, even though R0 is the one of the thing that we need. Instead of fetching instruction here, 3 right here, you're not fetching because you know that. By that point, you know it's a branch instruction, so you insert a bubble. So this becomes the bubble. Once you are finished with execute, like once you're finished with execute, this becomes the fetch. Decode, execute, memory, write back, fetch, decode, execute, memory, write back. Any question here? So the reason why we need to put the bubble right here is we need until at least this point where you know the result of the branch. And you then know, okay, I am actually now going to branch over here and over there. Why do we fetch, right? So the question is, why do we fetch right here, right? Is that the question? And not at 3. So the branch just, let me put it this way. Whenever you see the branch instruction, it doesn't screw itself, it screw the future instruction. Because you don't know for the future instruction you're trying to fetch, is that the correct path? Let's say you have if and else, right? If and else. The one that you can screw over is, are you running the if part or are you running the else part? That's the next instruction. That's instruction 3 and 4. Right? Because if you're not, right, if you're not going to execute instruction 3, which is this, what are the other instructions you're running? These becomes whatever instruction from the immediate, right? That goes to your instruction. Okay, so that's for the stalling. Blindly guessing is slightly better, right? Blindly guessing is slightly better. So what you do here is the same, right? So the same thing here. I'm gonna show this table because I think it's a little bit easier to understand. So when you blindly guess, right? If you guess correctly, if you guess the outcome of your branch correctly, this is what happened. You fetch, decode, execute, memory, and write back. Fetch, decode, execute, memory, and write back, right? And this is your branch. Let's assume that you guessed correctly and know exactly are you doing the if or the else part of your code. Instruction 3, because you're guessing correctly, fetch, here, decode, execute, memory, and write back. Fetch, decode, execute, memory, and write back. Right? Everything behaved perfectly because you guessed what PC to fetch. You guessed what PC to fetch. Any question here? By guessing, I mean that you're guessing that you're going to, let's say, run instruction 3. And in reality, it actually go to that instruction, not the other part. Okay, so what if you guess wrong? What if you guess wrong? This is what's going to happen. Fetch, decode, execute, memory, write back, fetch, decode, execute, memory, and write back. And PowerPoint always fight with me. I hate this. Okay, if you guess wrong, what happened to instruction 3? If you guess wrong, it would basically try to fetch instruction 3, right? And then in cycle 4, what happened after instruction 2 is in the execute? Oops, that's wrong. I kill this one off. Right? Then I'm gonna fetch the correct one. Fetch again. Yes, you fetch again, but now you know the correct PC. So you fetch it from the correct one. A totally different instruction. Fetch, decode, execute, memory, and write back. So this is the penalty. If you guess and you guess it wrong, this is the penalty, right? You need to get rid of whatever you fetch. What if you have more than 2 conditions? That becomes basically you would then resolve the condition, right? It's multiple instruction. So is this something like if I is less than 10 and j is greater than 20, right? Something like this. Is that your question? What if your if else is like that? So if your if else is something like that, when you convert it to assembly code, it's still one instruction that do the branch. This is what you do. First, you do if I is less than 10. Then you compute if j is greater than 20. And then there'll be an AND instruction, right? For this one and this one. And then you're going to do branch something that depends on this AND. So for switch case, same thing here, but it's you're going to end up with tons of branches. Depending on how you implement switch case, it can be a ton of branches, or if you remember the file pro, right, where you have this table, the jump table. Remember that jump table? So if you take file processing or system skill, in the assembly lecture, we talk in detail, quite a bit in detail, and including on the exam about jump table. Those jump are branches. So those are also branches. There are actually a paper that came out, and we usually, I think we usually cite about 10 to 20% of your code are actually branching. Right? A lot of time you actually jump or branch or some if else or switch case, and that also lead to a lot of jumps again, right? So a lot of your code are actually doing the branch. So branch prediction is an important topic. You want to make sure you do a really good guess, right? So one naive solution number 3 is educated guess, right? So let's say you write a code like this for I equals 0, I less than 100, I plus plus, right? For these type of for loops, if I'm gonna guess, I'm gonna take this branch all the time. If I'm gonna take this branch all the time, I will predict that I is going to be less than 100. How many times I'm going to guess correctly? 100, exactly. I'm gonna guess correctly 100 times, and incorrectly how many times? One time, right? When you exit the loop. So the way you write the program, some of them are making the branch easy to predict things like for loop over here. You can kind of like look at the code and like, oh, okay, this is going to be easy to predict. When you build the hardware, we're going to start talking about how we build the logic to make this guess. How many of you own a Samsung mobile phone? A while back? Okay. So Samsung used one of the branch predictor that use a really simple machine learning algorithm to guess your branch. It's really simple because you need to make this really fast. Most most logic for branch predictor these days get like really complicated because the cost of misprediction is really high. So we're gonna talk about it on Wednesday. Hopefully, this is a good primer on why you want to guess correctly. Think about it this way. Let's say you have 40 pipeline stages and you can't know what the outcome of the branch until stage 15. Right? Do they use AI to predict this? Well, I mean, the Samsung mobile phone has like a really simple machine learning algorithm to predict it. It's not complex. It's not complex. It's really simple. Something that would fit in your CPU. There are some push toward okay, what if you use some more complex machine learning? Yes and no. That are still like in the paper phase. Like we're trying to figure out if this is a good idea or not. Uh, some paper shows that this is potentially a good idea, but then someone would argue, what about the case where I start changing the program I run? Or what if the behavior of the program changed significantly? For example, you run things in the cloud versus run things on a machine, right? Uh, yeah, but those are common, right? Having a hardware specifically designed for ML. How many of you heard about Tensor Core? Well, this is like kind of lecture one, so I kind of gave you the primer already. The Tensor Core, the one that Google used for their machine learning, those are special design hardware that do matrix multiply. So we design special hardware all the time to actually serve different program, like some really common program done by designing something similar to this. Like you have the ALU and you know the data is going to get forward from here to here. So you plug in ALU and then ALU and ALU again, then you feed the data directly into different places. Right? In this class, like the whole semester, we'll talk about how to design what we call general purpose program. Right? General purpose program means your CPU. You can run any program on it, but be aware that there's also special type of hardware designed to do certain things. Bitcoin mining, for example, you can have a hardware that handle packet switching in a network. And so these days people talk about having the FPGA, which is the special design hardware that you can write your own hardware, put it to manage the network traffic. So these are really, really common in modern day computing, way more common than you think. Again, I'm gonna stress the fact that because Thailand is so behind on architecture, we don't have expert in this area at all, zero, until I move in here. We are really behind compared to other countries. Other countries use a lot of this. Like they start thinking about, okay, can we design a hardware? How can we design complex hardware to serve different purposes? I hope in the future generation there are more people to look into this area. Things like high performance computing, designing the chip, designing your own chip, designing your own chip to do different things. So if you're curious, for example, I've been working with Intel Labs in India, ETH Zurich, and Carnegie Mellon on creating this DNA sequencing hardware. Basically, you have this new DNA sequencing technology that generate a really long strain of the like ACTG, basically. That's matching. I'm gonna go back to something string matching problem, right? You're gonna map ACTG patterns to a different like source, which is also ACTG patterns to tell for these reads, we call it reads because it's a short string of ACTG, tell where do they map. And this string matching problem is actually computationally quite expensive. So what we do is create a new hardware that works inside DRAM. right? You when you buy DRAM, you can actually put some logic, like some compute processor, stick it next to DRAM, and then from that point, instead of sending the data to the CPU, that logic process the data, put it directly back to DRAM. So we get about, if I recall correctly, the number is about 100 times faster than using a GPU. And then, or maybe some 10x order of magnitude faster, and then a lot more power saving, about 100 times better in terms of energy efficiency. The paper will be presented next month in Micro, which is one of the top, like this is like best in the world for architecture venue. So that's one of them. That's hopefully that's give you something that, hey, I mean, we never talk about this in Thailand for sure. In Thailand, we talk about machine learning and hardware. I mean, machine learning and AI, right? All the time. So I think many of you might got sick of it at this point. Like, why machine learning? Why AI? And some of you are like, hey, good, so much money if you go into that area. A lot of other countries look into how to build the design. Oh, on Helix. I need to learn. I need to learn that part, the biology on that part first. But yeah, we can talk about it at least offline, maybe in office hour. For machine learning and AI, Google has their own hardware to run deep learning. Right, the one I talked basically is all about metrics, doing metrics multiply. They don't rely on GPU anymore. GPU is too slow for them. Huawei also tried to do that. I know Alibaba also tried to do that. Europe also tried to do that. I'm sure Intel in India tried to do that as well. Everyone is trying to do that. Trying to do basically things like machine learning, convolution. How many people sick of browsing Netflix and trying to find what you want to watch? Or spend more time trying to find what you want to watch than watching the movie or a series itself. Yeah. So we are building the hardware to make a better recommendation model. So hopefully you spend less time, right? Uh, there are a lot of groups trying to find like, okay, how can we make it more energy efficient, more performance, like perform better, so you can fit in more complex model. Because if you can fit in complex model, it means that hopefully it does a better job telling what you want. Right. So I'm working with one of the students in Shanghai Jiaotong on how to make this special hardware inside new type of memory. It's not DRAM anymore. We call resistive RAM. And this resistive RAM, the way it works is it follows the physics basically. It's V equals IR, right? I and R, I multiplied by R, those are multiplied. So you can do matrix multiply inside the cell. So we're trying to decide, okay, if we have this embedding table from recommendation model, which is the input, you need to do matrix multiply. So can we do that inside the memory, right? On its own, read it, and then repeat the same loop again and again and again really quickly. So those are some of the things that we are looking into. That I mean, we are looking as in like many countries are looking. Another thing that I look into. So these are stuff that I look into. So those are more like concrete examples, right? That I can give you. I'm working with folks from in Korea to kind of like, can we find a way to hack a GPU driver? So if you buy a fancy GPU, right, and you say, hey, I'm going to run some machine learning, and if you do deep learning, one of the problems you run into, this is a big complaint from the machine learning community saying, hey, the GPU doesn't have enough memory. And I know, yeah, it have like go 40 gigabytes or 12 gigabytes, depending on how much money you want to throw into NVIDIA, they're going to give you a certain amount of memory, right? But with that, what we're trying to do is if you buy a fancy GPU and you know that you're gonna not going to use all the GPU, can you actually hack the driver so that you can utilize unused memory on the other GPU as a intermediate steps between the CPU memory and the GPU memory. So those are more like system and hardware combined. Uh, Another team that I was helping a little bit was like, can we build a model to kind of predict how much memory you want, right? So that you can come up with a new hardware to have terabytes of GPU memory or terabytes of CPU memory. How can we make it reliable, right? Reading from 2 terabytes of memory is going to be more error prone than reading from 100 gigabytes. Uh, my research group back in CMU, one of the big things that we do, so we are one of the world leader in memory technology. And one of the things we do is called dealing with the error things like refresh, right? So if you look at my advisor work, you see that he works on tons of memory related topics. We come up with new type of memory. We look into the problem of like, okay, memory can be not, it can be insecure. You can hack something from the memory, right, by running some small instruction, right? I give you an example in lecture one. These things, right? What I can tell you in Thailand, after I've been here for a year, I'm sure of this, right? I'm 100% sure of this. We never look into building our own hardware. Whenever I talk to any vendors or any government, I was like, why do you want to build new hardware? I'm like, oh, you want to own the technology and you actually want to be a part of what people are working on. So right now it's still being undervalued, but it's interesting. Actually, it's fun to be like one of the people who spearhead this new area. It's not new. Computer architecture is one of the oldest topic in computer science, but then somehow this country like ignored. Uh, if you look at a normal, I start complaining now. I'm sorry, but if you look at a normal computer engineering program in Thailand, in Chulalongkorn Kasetsart, Mahidol University, those are not computer engineering that I know from CMU. It's more like computer science. There's a lot of hardware related topics that you guys are not learning. Right? So I hope that we can help a little bit, right, to catch up to what other people are looking. It makes the spectrum of what things you can do in computer science and computer engineering a lot wider. So you can work on different topics because everything in the end is related, right? If you want to do a big data workload, for example, you're going to run into a lot of I/O problems. You're going to run into a lot of memory problems. Don't limit yourself to like, how can I change the software? Why can't you just say, well, hardware sucks. Can I change the hardware? That's my life. Basically, I'm like, okay. It starts from me wanting to know how do I play a better video game. So I look into GPU design. And then I keep looking into GPU design, and then I basically try to figure out how do I make better GPU. To the point that I work with folks from NVIDIA on how to make a better GPU, right? And then it spanned from there. So hopefully these are some interesting example. I know it's really tangential to our lecture, and I know that I complain a lot about the situation in this country on the hardware knowledge in particular, right? We suck. Uh, Hopefully things get better. And hopefully I motivate you to like, at least if you don't care about the hardware, when you write a program in a way that is fast, right? If you know a little bit about the hardware, like, yeah, you can write the program to actually make it perform 3 or 4 times better. All right, so let's before we leave today, this is the part I want to discuss. We're gonna finish the lecture a little bit earlier. Right now it's 1:25. Do you want to do 5 minute break before we do a checkpoint? Basically, we're gonna move on to Discord. Each one of you would tell me where you are, so I know exactly. I'll tell you, you need to rush or you need, that's a night test. So I think you know what you're supposed to do and uh, whether there can be potential things that you might run into in a bit, right? So this checkpoint is for me to to gauge where you are. For assignment one, there's no points for the checkpoint, but if you meet my goal, you're gonna get extra credit of 10% of the entire of the assignment one grade. So if you meet the checkpoint, which is implement add and implement syscall, you get 10 extra percent of your full credit. So you're gonna get 10 points out of 100 by default. If you haven't finished that, I'm gonna tell you what are the potential problems you might run into. For all your friends who are listening to your other friends, feel free to chime in because from my point of view, I might see something as this is obvious and this is going to be a hard part. You might see it differently. You might see it as a, this is going to be a hard thing you run into, and you can give the hints to your friends. All right, so that's all for the lecture today. Let's do a 10 minutes break. At 1:35, we'll switch to Discord. Is that okay? All right, awesome. So I'm going to save the presentation and post the PDF on Canvas, and then I'm gonna save the recording, post all the recording to YouTube so they can watch it later. And then 1:35 we will be on Discord. All right, go get coffee. I'm sorry if we haven't had a break in the middle. I kind of like get traction on and stop. Sorry about that. So yeah, see you in about 10 minutes in Discord.